Okay, I'm continuing on this problem suggested to me by PaulGradenwitz, considering a observer at 1/6 of the explosion center. The observer only deals with his backward light cone and observes objects that appear to have a redshift. Okay, so let me go on to the next part of his question. I've already kind of gotten a start. I've written a function called shrapnel boundary events, and I used it a couple of times here to get speed, or it requests a speed. So for the black lines here, its speed is 1/6, and for the latter one, the speed is 1. So 1/6 the speed of light and 1 times the speed of light is essentially what's marked by that. And the boundary events, I can choose a number, but then what it does is it basically gives those gives them trajectories of cosine theta comma sine theta, and then just some stuff over here to make sure that the speed is applied. And then the third coordinate is just the time at which the appropriate event is counted. And so then depending on the number, it iterates. So I can change. Let's make that like 6 and see what. Change the number to 6, and you'll see how that changes the graphic. Now it's just got 6 events, and it doesn't look as nice because they're not circular. Or I could go all the way up to 100 and make it a really nice, make it look like an almost solid surface. So I decided on red to mark the photons, and black to mark the actual particles moving less than a speed of light. And I think maybe it's best that I make the red like 100 and the black like around 25. That'll make the most sense. Okay, now let's go ahead and read Paul's next part of the problem. He says, here is a picture that indicates what I talk about. He uses perfect circles, but with time dilations, something will come out a bit different. So he's using perfect circles to represent the what I call shrapnel debris. So what I'm going to do is switch those over to a more realistic pattern, if I can. It has the complete universe with objects moving with speed c at the outer edge with radius 1. That is represented in my space-time diagram by the red lines. So if we turn that, that's essentially what we're looking at, with this black circle corresponding to this black circle here at 1/6 the speed of light. Okay, and then it says inside a radius 1/2 with objects moving half the speed, and then a radius 1/3 and a radius 1/6. An observer is given with location on the radius 1/6 and with a radius equal to. An observer is given with a location on the radius 1/6 and with a radius equal to of equal distance 1/3. Okay, so we're going to have an observer here and an observer 1/6 and 1/3. Well, maybe he didn't draw that circle, but anyway, I'm going to go ahead and have an observer right here. We're going to look at it from that point of view. And we're going to go ahead and draw in these other two circles at 1/2 and 1/3. So for 1/2, we'll call this list 5, and it's going to be composed of just say 25 particles at distance 1/2. and we'll do list 6, which is the shrapnel boundary at 1/3. We'll have another 25 particles there. And then we'll make list 7 and list 8. List 7 is going to be a table like the one above, except it's going to be composed of list 5 and length of list 5. And list 8 is going to do the same thing as that, except it's going to use list 6 with a length of list 6. And then we're going to have to put that into our graphics. So we got list 4 black, point list 1, point list 2, point list 3, nope, list 5, comma, point list 6. Those are just events that we're using. And then line list 7, comma, line list 8, comma, and there we go. We've got basically three circles coming out from that. One at 1/3, 2/3, and 1/2 the speed of light. Okay, complicated diagram, but with all those lines in there. Okay, now a long moment of truth. I just want to do the thing. Basically, I want to perform a Lorentz transform on every one of these events, the origin and all of the events here. The first thing I need to do is maybe decide which point I want. Actually, I'm going to be basically picking out, transforming this, I think, to the left or the right, but the actual formula for it, and it's a matrix, is going to be a function of, yeah, I've been calling it varphi in Mathematica. It's CPHI. In LaTeX, it's just VARPHI. This is going to be the rapidity, and we're going to make the function where it's a matrix. It's a 3D matrix, comma. For this particular example, it's going to be a 3-dimensional matrix. It's got, and the matrix is going to, this one's going to be the Lorentz transform matrix just in the x direction. So it's going to be Cosh Cephei. We're going to use 0, 0. Or are we? No. Negative sinh Cephei. It's going to do basically nothing to the y variable, so we're going to just make that 0, 1, 0. And then it's going to do in the bottom area, it should be negative sinh Cephei, 0, Cosh Cephei. And that's the Lorentz transformation. It's doesn't look like a matrix here, but if you drew it out as a matrix. And then what we're going to do to each of the events, first we're going to calculate what the rapidity needs to be, which is arctangent of our velocity of 1/6. And can't remember whether that's going to make it go to the right or the left, but either one will work fine, because we've got actually not exactly either one because I made it 25 instead of 24. If it had been a nice even number, then either one would work. But this one might not put a particle right at dead center. And this is going to be kind of repetitive. I could make this more efficient if I had a little more time, but I'm just going to make list one BLT matrix parentheses rapidity of dot list one, and I'm going to do that with all of them. 2, 3, 4, 5. Oh, and then I'm going to have to completely redo. I'm just going to do this on the events, of course. So list 2, list 5, and list 6. And then that's going to be done on list 1, list 2, list 5, and list 6. And I might be having a problem with this. Yeah, I think it's not quite. I'm pretty sure I'm going to have to do transpose list 1 over here, and then at the end transpose again, because the way I've set up those matrices, it's not appropriate for matrix multiplication as is, but if you do a transpose, it makes it. Okay, you can see something has happened. Looks like something has slanted. Yeah, okay. Now at this point, I need to do an additional thing because I haven't lined up the lines correctly. So let's come back. I'm just gonna take list 7, list 3, list 4, and list 6, and list 7, and list 8, and put them down here. List 3, list 4, list 7, and list 8. Bring that down so, oops, so that those connect up, hopefully. And boom, now it's nice and smooth. Okay, so this is the Lorentz transformation of the situation here. When you do the Lorentz transformation on those events, and what you can see here is that what was, maybe you can't tell. Okay, yeah. Okay. What was a straight line before is now this line here. This is the stationary point. You can't really, I guess you can't tell which one is stationary, but you can see kind of looking down. This is the stationary point, and then all of these lines go off in different directions. Now, if you wanted to see what that explosion looks like, I wonder if I can get Mathematica to draw either a plane through that. Uh, it's kind of awkward at this point because if I draw a plane through this, it'll catch these ends because those events happen before this one, but it won't catch these events because this event happens after those. But I could drop a past light cone from there to see kind of the places where those world lines of those particles pass or cross the observer's past light cone, which would mean that he could legitimately see them. And it looks like there is a graphics primitive called cone. Extends from 0.0, 0, to 0.1, 1, 1 with a radius of 1/2 at its base. So if I wanted to represent this in this diagram, I'm going to want the past light cone to be start at 0, 0, 1, or CT. Actually, I want it to be CT because that's what I've been using as the current time. And the event 0, 0, which is the origin down here, and 1 to be the radius. No, I want CT to be the radius. And you know what? I'm just gonna make it a small light cone of just 1 times C, 1 times C. Of course, that is the scale of our diagram, so C times 1. And boy, did that come out ugly. Looks like I need to change that cone. There we go. I changed it to a green with opacity of 0.1, and now you can see, you can kind of see the events that this guy would be currently seeing. It's not coming out great, but in order to actually kind of like really answer this question, you need to be able to solve where these black lines intersect with this green cone, and that would tell you exactly where, kind of exactly how this guy that's at the point of that cone would observe the distribution of those particles through the space. You could also ask the question, where would he calculate they are now according to simultaneity, which would, instead of being where the cone intersects, would be the plane of simultaneity at any given point for that guy. And there might be a pretty simple formula, like it is all hyperbolic geometry. So in practice, it's probably not a whole lot more difficult. I mean, if you knew how to do it, it probably wouldn't be much more difficult than any problem in ordinary trigonometry. But right now, I don't know exactly how to approach the problem. Anyway, thank you for watching.